All right, welcome everyone, especially to Mr. Elvis Paredes' class at Colegio Bilingüe Cuscatán. Today, we're diving into something super cool, the applications of thermodynamics. Ever stop to think about how a car engine actually works? Or how a refrigerator can somehow be colder inside than the room it's sitting in? Well, it all boils down to thermodynamics, and we're about to see just how it powers, well, pretty much everything. Okay, so here's our game plan. We'll kick things off with turning heat into work. Then we're going to flip that around and look at moving heat uphill. After that, we'll get into the efficiency challenge, why nothing is perfect. And finally, it's your turn to practice. Sound good? Let's go.
Seriously, you might not even realize it, but this stuff is happening all around you, all the time. The principles we're about to break down, they're the secret sauce, the magic, behind so many machines you use every single day. Yep, we're talking about everything from the car that gets you around to the fridge keeping your food from spoiling.
All right, first up, turning heat into work. Let's talk about the power of the heat engine. So, what is a heat engine? Well, it's pretty straightforward. It's a device whose whole purpose in life is to take heat, thermal energy, and turn it into actual work, into motion. Think about a car's gasoline engine, a giant jet engine, or even the steam turbines that make our electricity. They're all basically just heat engines at heart.
Okay, so let's break it down. Step one. It all begins with a bang, literally. You've got fuel burning inside a cylinder, right? That combustion creates this massive blast of heat. This heat gets pumped into the gas that's trapped in there, making its temperature and pressure just skyrocket.
Now that gas is super hot, super high pressure. It's gotta go somewhere. So what does it do? It expands, and it expands with a ton of force, pushing a piston out of the way. And that push, that's it. That's the work. That's the magic that eventually makes the wheels on your car go round and round. But, an engine that only fires once isn't very useful, is it? To get the piston back to where it started so we can do it all over again, the engine has to get rid of some of that heat. It basically exhales this leftover waste heat, and that allows the whole thing to reset. This is what we call a cycle. It's designed to repeat over and over and over again. In this little schematic here, it's the perfect way to visualize the whole process for any heat engine. Think of it like this. It lives between a hot place and a cold place. It pulls in heat from the hot source, we'll call that QH. It uses some of that energy to do useful work, that's W, and then it has to dump the rest of the heat, the waste heat, QC, into the cold place, like the air around it. Hot in, work out, cold out. Simple as that. Okay, so we've seen how to get work from heat, but what if we wanted to flip that script completely? What if we wanted to use work to move heat around? Let's check it out. Yeah, this is where things get really interesting. A heat engine, well, that's kind of like heat flowing downhill naturally from hot to cold, and we just tap into that flow to get some work done. But a heat pump or a refrigerator, that's the complete opposite. We're actually using work to force heat to go uphill from a cold place to a hot place. It's fighting against the natural flow of things. And the perfect example of this is your refrigerator or your AC unit. They both have these four key parts. First, a special liquid inside absorbs heat from the cold part, the inside of your fridge. Then a compressor gets to work squeezing that liquid and making it super hot. Next, that hot liquid flows through coils, usually on the back of the fridge, and releases all that heat out into your kitchen. Finally, it goes through an expansion valve, gets really cold again, and is ready to go back and grab more heat. It's a continuous loop of heat grabbing and heat dumping. So this all leads us to a really, really big idea. A fundamental rule of the universe, really. And that's the challenge of efficiency. Okay, so when we talk about how good an engine is, we use a term called thermal efficiency. All it really is a number that tells us how much of the heat we put in actually got turned into useful work coming out. It's like a performance score for the engine.
And the formula couldn't be simpler, really. Efficiency is just the work you get out divided by the heat you put in. What you got divided by what you paid for. That's it. A super direct way to measure how well it's doing its job.
So that brings up a huge question, right? Why can't efficiency ever be 100%? Why can't we just build a perfect engine that converts all of the heat it takes in directly into work? What's stopping us? Well, the answer is one of the most important laws in all of physics, the second law of thermodynamics. It basically says you can't. You just can't. Some energy is always going to be lost as waste heat. That heat that gets dumped into the cold reservoir, it's not optional. It's a fundamental, unavoidable tax that the universe charges on turning heat into work.
All right, you've learned the concepts, you've seen the formulas. Now it is time to practice. It's your turn to be the physicist. So for these next couple of problems, go ahead and pause the explainer and see if you can solve them on your own.
Okay, here's the first one. A heat engine gets 1.0 times 10 to the 4 joules of heat and releases 7.5 times 10 to the 3 joules. So how much work did it do? Go ahead and pause here, do the math.
How'd you do? The answer is 2.5 times 10 to the 3 joules. Remember, the work is just the difference between the heat you put in and the waste heat that comes out. So it's just a simple subtraction problem.
All right, ready for round 2? This time, we're calculating efficiency. An engine takes in 6 kilojoules of heat and produces 4.8 kilojoules of waste heat. What's its efficiency? This one has an extra step, so think it through. And the answer is 20%. So first, you had to find the work done, right? That's 6.0 minus 4.8, which gives you 1.2 kilojoules of work. Then you take that work, the 1.2, and divide it by the total heat that went in, which was 6.0. That gives you 0.20, or 20% efficiency. Nice work.
Okay, so let's do a quick recap of the big ideas. Number 1, heat engines use heat to do work. Simple. Number 2, heat pumps are the opposite. They use work to move heat. Number 3, the big one, the second law of thermodynamics says you can never have 100% efficiency. There's always waste. And finally, number 4, we measure that performance with a simple formula. Efficiency equals work output divided by heat input.
So that leaves us with one last thing to think about. We know perfection is impossible, right? We know some energy is always going to be lost. So the real question for engineers and scientists today is, knowing that, how can we get smarter? How can we design more clever, more efficient systems to build a more sustainable future, all while playing by the universe's rules?
And that's our look at the applications of thermodynamics. Great job today, everyone. Thanks for joining me.